This is Unit 3, and this is our second FRQ. A block sits at rest on a horizontal surface. One end of a spring is attached to a block, and the other end of the spring is attached to a wall, as shown in Figure 1. The block is initially at position x is equal to 0, where the spring is at natural length. The block is then pushed to the left, compressing the spring. The block is released from rest from the position x is equal to negative a. All frictional forces are negligible. Consider the system that consists of the block and the spring. Figure 2 shows an energy bar chart that represents the kinetic energy and the elastic potential energy of the system when the block is released from rest at the position x is equal to negative a. Draw and shade the bars that represent K and U as spring potential energy of the system to complete the energy bar charts shown in Figure 3 for when the block is at position x is equal to 0 and x is equal to a over 2. So for energy bar charts, first, we can determine for x equals to negative a. So this is when you are at release. At release, this is when you have k initial is equal to 0 because of the fact that velocity is equal to 0. And then when you have a spring compressed by a, you're going to have USI is equal to 1/2 KA squared. Therefore, your total is going to be equal to 1/2 KA squared. So this is going to be, now this expression is going to be constant for all of our positions, each one of these graphs, each of these scenarios. So now for at x is equal to 0, at x is equal to 0, we can represent when the spring is unstretched, we have US is equal to 1/2 K times 0 squared is equal to 0. If we use energy conservation, then we know that K is equal to the total energy, which is equal to 1/2 KA squared. So what we can draw is we can draw the potential spring energy is going to be a horizontal line at 0. So, and our K bar, okay, kind of like this. Our K bar is going to be a bar that is the same height as the original bar, but just at x is equal to negative a. Oh, just at not at x is equal to negative a, x is equal to a. So here, now for the last case at a over 2, we know that the spring is stretched by a over 2. So then you can write that the spring potential energy is equal to 1/2 of K times A over 2 squared. So US is equal to 1/2 K times A squared over 4. US is equal to 1 over 8 K A squared. So then your total energy is going to equal to 1/2 K A squared. So therefore, you can write your kinetic energy is equal to E minus spring energy. Now this is going to be, let's move this down a little bit. K is going to equal to 1/2 KA squared minus 1 over 8 KA squared. So that's going to equal to 4 over 8 KA squared minus 1 over 8 KA squared. K is going to be equal to 3 over 8 KA squared. Now at a over 2, we can draw our total height is going to be the same as the original because there's conservation. So it's going to be the total height always going to be the same because you have conservation of energy. So it's always just going to be teetering back and forth between different forms. So the US bar is going to be 1/4 And then the K is going to be 3/4. So, and that's because and now the mass of a block is m, and the spring constant of the spring is k. Starting with the conservation of energy, derive an expression for the speed of the block as it passes through position x is equal to a/2. Express your answer in terms of m, k, and a, and physical constants as appropriate. So, what we know is we can start with the conservation of energy. If we start with this, we always have that the initial is equal to the final. So we have 1/2 Ka squared is going to be equal to, so you can also write this as so this is US is going to be equal to kinetic energy plus US. So you can write this out, that's going to be 1/2 mv squared plus 1/8 Ka squared. Now you can subtract 1/8 Ka squared, and also this. Now, if you do this, you have 1/2 Ka squared minus 1/8 Ka squared is equal to 1/2 mv squared. 4/8 Ka squared minus 1/8 Ka squared is equal to 1/2 mv squared. 3/8 Ka squared is equal to 1/2 mv squared. Now multiplying by 2. We have that 3/4, because 2 times 3 is 6, 6/8 is 3/4. Now you have solving for v squared, just divide by m. Now taking the root, okay. Figure 4 shows a graph of the total mechanical energy of the spring block system as a function of the position of the position of the block x. On figure 4, sketch and label a graph of the kinetic energy K and elastic potential energy US of the system as a function of the position x on the block. So we know that we can write elastic potential energy as USX is equal to 1/2 kx squared. So this is going to be a parabola opening up. Now, for kinetic energy, you can represent this as k of x is equal to E minus US. K of x is equal to 1/2 Ka squared minus 1/2 Kx squared. K of x is equal to 1/2 Ka squared minus x squared. So this is a down parabola. So now, for our axes, our horizontal axis is position x, and our vertical axis is our energy. So we can mark negative A, we have negative A over here and positive A over here. So for the elastic potential US, it's going to be upward parabola. So at x is equal to 0, you are going to have that US is equal to 0 as a point. So at your x value of your x is going to be horizontal position. So at your x is equal to 0, you're going to be at 0 as well. So then at x is equal to positive a, you're going to have that it touches, it's going to be, okay, when it's, and then at x is equal to negative a. Okay. And then here we're going to have the points at x is equal to 0. You have that's your max. And then so it touches 0 at plus or minus a, and it peaks at x is equal to 0, and it's going to be symmetric as well. Indicate how the total mechanical energy would change at x is equal to a over 2, if at all, if there were non-negligible friction between the block and the surface. Briefly justify your response. So we know that if friction exists, then you have net external forces and no conservation of energy. When that's the case, mechanical energy will decrease over time. And then kinetic energy at x is equal to positive a over 2 is smaller. We also have that the friction does negative work. Friction is less than 0. Therefore, we have our E final is equal to the E initial plus the work of the friction, the work done by friction. And we also know that since our work is negative, it's negative because it opposes direction of motion, because that's the definition of friction. That means that the final energy is going to be less than the initial. Thus, we have that K at I over 2 decreases.